Try to calculate the value of sine of 12 degrees. Now, use the calculator. But the question is, how does it know? And how does it know so fast? You're probably thinking about the formula from school, the Taylor series that defines sine, theta minus theta cubed over 6, so on and so forth, forever. It's a perfectly good definition, but that's not what the calculator does or is even capable of doing. Because this series runs on multiplication, and the chips inside the first calculators, along with some of the chips still being made today, cannot multiply. In fact, it can hardly do anything beyond adding two numbers or sliding a number's digits one place sideways, which in binary is the same as doubling it, or halving it. Add and half, that's all it knows. Out of adding and halving, the two most basic things that even a toddler can do, something has to magically find the value of sine of 12 degrees. A smooth, curving value, magicked out of the math skills of a 6-year-old, and handed back in an instant. The trick that does this has been hiding inside almost every calculator ever built. Let's rebuild it, from scratch, together. It was 1959. An engineer named Jack Folder was working on the navigation system for the B-58 Hustler, a bomber that flew at twice the speed of sound. A plane moving that fast has one big problem. It has to know, at every single second, exactly which way it's pointed. The machine doing that job was an analog computer, a box full of spinning parts and moving voltages. And the trouble with a box like that is that it drifts. On an aircraft where a small error in heading turns into miles of error on the ground, it's not a simple error. So Volder needed the answer done digitally. Real trigonometry, computed fresh, fast enough to keep up with the airplane. And he needed it out of the simplest hardware anyone could build. Because in 1959, there wasn't anything else. No multiplier, no lookup tables worth the memory they would have cost. Just registers, an adder, and the ability to shift bits sideways. He found a way. He called it CORDIC. And the whole thing turns on one idea that sounds, for the first time you hear it, like it cannot possibly be enough. To rebuild sine, we have to stop thinking of it as a function and go back to what it actually is. Start drawing a circle with the radius 1. From the center, draw an arrow out to the edge and swing it up to an angle, like 12 degrees. The tip of that arrow now aims at a single point. But how high up is it? How far above the middle does that tip sit? That height is the sine value. So watch what this does to the problem. The calculator doesn't actually need to evaluate a function. It needs to take an arrow lying flat and turn it until it points exactly 12 degrees up, and then measure the height of its tip. Which means the real question was never, how do you compute sine? It was this. The question is, using only add and half, how do you even rotate an arrow? The first thing you think of is to look it up and use the formula for rotating a point. Turn it by some angle, and its new coordinates come from the old ones, mixed together using the sine and the cosine of that angle. But to rotate by an angle, the formula needs the sine and the cosine of that angle, the exact two numbers we wanted to find. To turn the angle, we'd already have to know the answer, so we're stuck in a loop. You've got an arrow pointing right, you can only add and half, you can't multiply, and you can't look up a single value of sine or cosine ahead of time. How do you turn that arrow into an exact angle? The way out is kind of cheating, but it's still genius. We don't rotate by the angle we were handed. Instead, we only ever rotate from angles from a short list we picked in advance, which is chosen for one property. Using the attempt to turn needs no multiplication at all. We can't reach 12 degrees in a single turn. We can get there with a sequence of smaller turns, with every turn coming off one fixed menu. The first angle on the menu is 45 degrees, the next about 26.5, then 14. Each one is about half the last, approaching towards 0. But why those angles? Because each one is an angle whose tangent is exactly 1, or a half, or a quarter, 1 over a power of 2. When the slope of your turn is 1 over a power of 2, the multiplication inside the rotation is the same thing as halving. The first turn doesn't need to be halved at all. The second, half once, so on and so forth. Slowly, out of nothing but adding and halving, we build our way to the angle we wanted. The arrow starts flat, at 0. Since we want 12, turn by 45, which is way too much. Then the next turn goes down by 26.5, so about 18. Still too high. And on it goes, each turn smaller than the last. Every step is a single yes or no. Turn up or turn down. Add the next angle or subtract it. And because every angle is about half the one before, every decision cuts the leftover error in about half. It's a binary search, but it's used as an arrow. 10 turns bring it within a tenth of a degree. 40 and becomes correct to 10 decimal places. But the arrow is hiding something. We cheated, so there's a price to pay. A true rotation leaves the arrow just as long as it started. Ours doesn't. Every one of those turns doesn't just pivot the arrow, it slowly stretches it, a little each time. So after 40 turns, the arrow points the right way, but has grown far too long. The tip of its arrow becomes too high. So we have to figure out how much is stretched. Start with a single turn. Turn up or turn down. The stretch is exactly the same. Now follow that all the way down. If every calculation takes the same amount of turns, then every calculation stretches the arrow by the very same amount. One fixed number, identical for 12 degrees and for every angle you ever ask it for. It comes out to about 1.647, and its reciprocal 0.607. It's directly etched right into the strip. So the entire correction for all that stretching piled up across every turn is one step at the very end. Shrink the arrow by that one stored number, and because even that can be folded back into the same halving and adding we started with. So do it. Scale the arrow down. Read the height of its tip, 0.0208. The sine of 12 degrees, built from the first step to the last out of nothing but adding and halving. Now, what we've built is way more than a way to find sine. We ran the arrow forwards, put in an angle, read out a height. We can also run the same machine backwards. Start with the point sitting somewhere out in a plane, and this time, instead of chasing an angle, push the arrow to drive that point down onto the axis, flattening it one turn at a time, while you keep a running total of every angle you spend. The instant the point lays flat, that total is the angle it started at. You computed the inverse, arctangent. And the distance the chip had to travel, that's just the point's distance from the center, the square root of x squared plus y squared, so the arrow can now take square roots. Then, in 1971, an engineer named John Walter developed this further. Take the arrow's world and bend it. Trade the circle for hyperbola, flip the single sign in one place, and the same menu of add and half steps begins pouring out completely different functions. Natural logarithms, powers of e, plane multiplication, division, all of it. One arrow turning through changed geometry. And for its first years, that idea lived exactly where you'd expect. In military hardware, in navigation boxes, in places nobody outside the industry ever saw. Then, in 1972, it slipped into the palm of a hand. The HP-35 was the first handheld calculator that could do trigonometry. And this same spinning arrow was beating inside of it. Before that machine, a student who needed the sine of an angle opened up books. Rooms full of human computers, grinding through arithmetic for years, all so that someone later could look up a number. The HP-35 replaced all of it with a warm little chip, doing the two most simplest things it knew how to do. Add and half. Point an arrow, turn it a little, the only way it knows how. And the most grateful functions we have fall right of the machine, as nothing more than the height of its tip. Make sure to like and subscribe and watch my other videos. Peace out.